Okay. Let's begin here. Oops, I need that too. Alrighty. So, from the warm-up, okay, you kind of got an idea about, what we're going to be getting into today and tomorrow. And there's no real reason, for including it in this unit other than just it has to go somewhere, and it's not enough to really warrant its own unit. So, thanks. Unfreeze. So, we're going to talk about the sequences and series tomorrow and today. All right, today we're going to look at a specific kind of sequence. So a sequence is just a list of numbers. So when you looked at the warm-up earlier, right, that we had, most of those were just sequences, right? Just a list of numbers that have some sort of, that hopefully have some sort of meaning behind them and how you find the next ones and stuff like that. Okay? And then we'll talk about a series in a second here. The specific kind of sequence that we're going to talk about, we talked about the Fibonacci sequence, right? That first one was the Fibonacci sequence, so it was so special it was named, right? And so we have certain kinds of sequences that occur every so often, or that show up enough that we can then give them names. Okay, or they are named. Okay, we didn't name them, but we don't give them the names. So this specific one, right, is an arithmetic sequence we're going to talk about today. Does anyone remember what makes an arithmetic sequence? And again, I don't know. I know that word is also pronounced arithmetic too, but I think when it comes to like an adjective, I feel like arithmetic is better. Yeah, so I'm trying to confuse you. But it is the same word. It's the same word as arithmetic. So a sequence of numbers whose difference between consecutive terms is constant. Okay, that's an arithmetic sequence. Probably one of the most basic ones you learned about, or you ever did back when you probably were in elementary school or something like that. The last time you probably worked on arithmetic sequences was in Algebra 1. So for many of you, that might have been middle school or 9th grade, right? So it could have been a little while ago. Alrighty. So, for example, all right, here is an arithmetic sequence. Okay. Question? Yes. Feel free. That's fine. That's okay. I'm sorry. I'm sorry for you. I know you like your colors. I do. So 3, 7, 11, 15, right? Okay. And before we get into what the actual pattern is here, I want to describe a few things. So 3, right, that is designated as first term, or term 1, right, because it's the beginning of our pattern, our sequence here. And so one way we symbolically represent the first term of a pattern, okay, is we say, yeah, isn't that crazy? You can take the whole box if you want to and look through it. We represent it with A sub 1. And so then, of course, the next term here will be A sub 2, and then A sub 3, and A sub 4. Okay, on and on there. Okay, and then, of course, we could go out and have A sub n. And then the next term after A sub n, how we designate the next term after A sub n? It would be A sub what? N plus 1. All right, and then we can, A sub n plus 2, and so on and so forth there. Okay, for these like more generic terms, the nth term, the n plus 1th term, so on and so forth. Okay, and the reason why we're covering this topic again in pre-calculus is because it shows up in calculus, believe it or not. Okay, if you take A, B, C. If you just take A, B, you'll see a little bit of this sequence and series stuff, but it's not until A, B, B, C where you'll see this kind of thing. Well, I'll actually get to that in a second. Never mind. Okay, it doesn't happen with sequences. You have to understand sequences before you can talk about series. Now, what is the pattern here? Plus 4 each time, right? We are adding 4 every time there, right? There we go. We're just adding 4 every time. So in other words, another way to say what's the pattern here is you can also say what is the common difference, or what is the shared difference between terms here, which is 4. We're adding 4 every time, right? So the difference here would be 7 minus 3, 4. 11 minus 7, 4. 15 minus 11, 4. Okay? So the common difference... Question?
Look at your door.
Can I get my door?
Look at your door.
Oh, yes.
That looks really scary.
We just need some like zombie groans. Brains. All right, so the common difference is a sub n plus 1 minus a sub n. So it's a next consecutive term. It's like the next term minus the previous term. Okay, consecutively speaking. Okay, so in this case, right, we can pick any two numbers and subtract the next one. Sorry, do the previous one subtracted from the next one. So 11, minus 7 as an example there. It's 4. Okay, so you can see the idea of common as in shared, right? Shared among everybody kind of thing. And then difference, well, subtraction, right? Common difference. So what would a sub 5 equal? 19, right? We'd add 4. And then what would a sub 6 be in this? 23. And then what would a sub 100 be? Yeah, so that's part of the problem. Was that? 399? It would be 399. Very good, Rohan. Yes. Okay. Mathemagic. So the problem is here we run into a situation where the way we're currently kind of developing this sequence is done what it's like actually has a mathematical term for it. It's called recursive. So this is we recursively define this function by saying, oh, you add to get the next term, you add 4 to the previous term, right? That's recursive, okay? Because we keep using that reoccurring pattern there to do it. Okay, so you keep adding 4 every time, and you get the next term. But the problem is, if you want to skip a bunch of terms, in order to find the 100th term, we need to know what the 99th term is. But to find the 99th term, we need to find the 98th, and we have to find the 97th, and so on and so forth, all the way back down until we get to something that we know, and we can just keep adding those 4s on, kind of thing. But there are shortcuts, right? Like Rohan illustrated there, because I'm assuming you didn't write out all 100 terms there. Okay, I'm not going to check your paper. I'll take your word for it. But anyway, so to find the nth term, okay, of an arithmetic sequence, so the nth term as in a generic any number term, okay, so you want to find the millionth term, if you want to find the 20th term, to find the nth term, and you may remember this formula from Algebra 1, or you might not, because it's been so long. Oops. Okay, there we go. So it is equal to a sub n is equal to a sub 1 plus n minus 1 times your common difference there. Okay, so that's what we want there. Just get rid of that. There we go. Flawless, except now I just have this like big gap between my parentheses and my n, but that's okay. All right. So what are the different pieces here? We need to know because there's a lot of variables in here, right, for some simple pattern. So a sub n, that's what we're looking for. It's the nth term, right? It's whatever term we're looking for. You could replace the n with the 100 in our case because we're looking for the 100th term, right? A sub 1, we know that is the what? First term of our pattern. Okay. And then n, that's just the number of the term. So for example here, if I want to do the 100th term, I would have a sub 100, and then 100 go in for n here, right? Number of the term. And yes, D, what do you think that stands for? Common difference. Common difference. Okay, and again, only arithmetic sequences have a common difference, right? They only arithmetic sequences have a common difference. Okay, where you add or subtract the same amount each time. It's really a common difference there. Okay, so let's do it for a sub 100 here and just check Rohan's work. Okay, so what is our first term in the sequence that we started with here? 3 plus, and then parentheses, the number of the term, it's 100, right? So we're going to put 100 in for the n. And then what was our common difference for the pattern again, for the sequence? A positive 4, so we'll put the 4 in there. Okay, and now it's just a matter of doing the mathematics. Okay. You could do 100 minus 1 and then do 99 times 4, but I prefer to just do 4 times 100, which is 400 minus a 4, right? Distribute there. So 400 minus 4 is going to be 396. And then plus 3 would be 399, as Rohan said there. Okay. On the test, will you need to know this formula? No, you will not. I will give it to you. Sorry about that. Silence phone. Okay, so that's our answer then. All right, so here, let's do one more here, and then I'll do a few more things. One more example with this. All right, so let's write an equation for the nth term of the sequence. Okay. So a sub n then. So we want the nth term. We want just the generic nth term. So we're going to use n, right? We're going to use just n for our variable there. So a sub n equals, we still have the same first term of 3. Again, since we're not finding a specific term, we're just kind of come up with a generic, kind of formula here. We'll just do n minus 1 there. And our common difference, though, for this pattern is still times 4. Okay? And this is perfectly legitimate if you want to leave it just like this and say, okay, there's a formula for the nth term. But we could distribute the 4 here and then combine like terms. And so we get 1 plus 4n for our a sub n there. So 1 plus 4n is our, did I do? Negative 1 plus 4n. Goodness gracious. Negative 1 plus 4n is our nth term formula. So now, if I said, what's the 1,000th term, you just plug 1,000 in for n there. Okay. By the way, this format here, a sub n equals negative 1 plus 4n, that looks a lot like what kind of form that we've used for, what's that? Yeah, it's a linear function. Exactly right. Arithmetic sequences are linear. They are linear, right? And so there's our y-intercept, there's our slope. Notice the y-intercept here is negative 1. But our first term was 3. That's kind of weird, right? Don't we normally start with our y-intercept? So why didn't our pattern here start with negative 1 and start with 3?
It does.
Because it does. That's certainly an answer.
Just minus 4.
Okay. What's the number of the term? Actually, let's go back here. What's the number of this term? What's 3 is the what term? First.
But
What's the 0th term? Exactly right. The y-intercept is like the 0th term. So you kind of have to either go back 1 if you want to use just like slope-intercept form here. You have to go back 1 in the pattern to get the 0th term. Okay. And why is that? Remember, because the y-intercept is associated with the x-coordinate of 0. This point would be associated with the x-coordinate of 1. So you can think of this as the point 1, 3, then 2, 7, then 3, 11, then 4, 15, so on and so forth. All right. So, anywho. Okay, so we're going to write an equation. For the arithmetic sequence. And we're going to find the 20th term. Okay, so we're going to write an equation now for the arithmetic sequence that I'm going to give you, and we'll find the 20th term. All right, so first one, a sub 1 is equal to 5. What does that mean again in the context here? The first term of our pattern is 5. D is going to equal 4. Yeah, I know, not very different here. But what does D stand for again? Common difference. That means that's the number we're adding every time. So in other words, we could start with 5, and the next one would be 9, and then 13, and so on and so forth. All right, so we're supposed to write the equation. So a sub n equals 5 plus n minus 1 times 4. Okay. And if we distribute and combine like terms here, we'll have 4n and then minus 4 plus 5, 4n plus 1 now. Okay. And so this is an example of how the pattern could be given to you, right? It might not be given to you as like a sequence, like a list of numbers. It might be given to you just in the important parts, right? And then from that, you then develop the formula from that. Or from that, you develop the formula. So then now we're going to find the 20th term, because that was the other part of the question there. We're going to put that 20 in for n. So it'll be 4 times 20 plus 1, which is 81. Okay. Bless you. Bless you again. Okay? Easy peasy, right? Easy peasy. Well, let's try another one. A sub 1 is equal to negative 4. And A sub 5 is equal to 16. All right, so now what information are we given here? A sub 1 is the first term, so it's negative 4. And A sub 5 is the fifth term. Okay. So we're supposed to write an equation for the arithmetic sequence. So in order to do that, let's see here. I'll need A sub n equals. Okay, we have our first term there. It's going to be negative 4 plus n minus 1 times the common difference. What's our common difference going to be here? Yeah, we're not told explicitly, but we can figure it out. So how can we figure it out, though? What can we do here? What's some options we could use? Yes, Jen? Ah, okay. So we could use one of our points here, okay, and then solve for the variable d. Yeah, so that's one way to do it. Exactly right. Okay, so you can use the a sub 1 equals negative 4, or you could use the a sub 5 equals 16. Your choice. Either one will work. Okay, so let's go ahead and just use the 16 because that's what you said, right? Jenna wants to use that one. So let's see here. It'll be 5 minus 1 times d there. Oops, I should have put the 16 in for the a sub. I can do that now. So 16 equals, let's see, we'll have negative 4 plus 4d. So add the 4 over, we get 20 equals 4d, and then d equals 5. Okay, so finally we got our common difference there, and so we can say then a sub n equals negative 4 times, no, a sub n equals negative 4 plus n minus 1 times the 5. Okay, like so. The common difference, as it turns out, it is the slope, too. So another way you could have done this is just use the slope formula with the points 1, negative 4, and 5, 16. Okay, and just do the slope formula there. That'll also get your common difference, too. All right. So anyway, there's our equation for the arithmetic sequence, and we'll find the 20th term, so we'll just plug in 20 here. It's your choice whether you want to simplify the sequence before you plug in, or if you just want to, put it in the way it's written there. Your choice. Okay. So 95 minus 4 equals 91. Okay, and this is also part of our answer there too. Okie dokie. Questions on any of that? So far, so good. Does anyone remember this from Algebra 1 at all?
Yeah.
Yes? Bad memories? Algebra 2 maybe even? Okay, I don't remember. I forget. It's been, I taught Algebra 2 last year, but I forget. 2 years ago. Yeah, 2 years ago. Okay. Not quite done yet, though. Not quite done. Okay. Here's one for you to try. Or am I going to make this too hard? Let me think here now. Will this be too hard? Yeah, never mind. This one's going to be too hard if I do that. Well, maybe not. I'll have you guys try about it. Yeah, I'll have you try. Okay, write an equation. Same directions here. Write an equation for the nth term. Find a sub 50. Okay, and here's our information. A sub 2 is equal to 10. A sub 7 is equal to negative 20. Okay. A sub 2 is equal to 10. A sub 7 is equal to negative 20. And I'll write up the okay, there's our arithmetic sequence formula there to help you out if you need it. And you will. As Stephen said, this is linear, so you can use, what you know about writing equations of lines here to help you, okay? Again, that a sub 2 is equal to 10, that's like the point 2 comma 10. And a sub 7 equals negative 20, that's like the point 7 comma negative 20. Okay, so you can use that to your advantage there. Okay. The x value is like the number of the term, the y value, the output is like the term itself, what the term is. That would be a helpful calculation. Wonderful. There's like, see how there's like the, I don't know, third shelf up from the ground over there. You might have more room if you go. Sorry. Too fast and furious. There we go.
Would the slope be the A1 or the D?
So the A sub 1, remember, is the first term. So D, which is the common difference, how you're changing every time, that would be your slope. So question? Yeah, just on the shelf there, please. Thank you, Cindy. Thank you, Bob. Thank you. Stuck, need some help. Want me to come look at it? Blaine? Yes? Well then, your 50th term is correct.
I had something else.
And your first term is correct.
It's just so rich.
Your first term is correct, Roman, and your common difference is correct. Oh, yeah. Just add it, make it into something. Yes. Nice, although. Yeah, that's right. Yeah, you're all right trying there, Chrissy. Good job. Good thinking. Yes.
We did it like 2 different ways. So this is my way, that was my way. It was all right.
Oh, I see. Yes.
Yeah, so like we're trying to do different answers and like work with the math.
Okay. There are many ways. There are many ways. There are many ways to arrive at this. So, like, one way is like, okay, we only have 2 terms, and one of them is not the first term. So one way you could do it is say, all right, if our second term is 10, so I left a blank for my first term, second term is 10, and then I left a couple more blanks to the 7th term, which is negative 20. And you can see, okay, I have to take 5 steps here, 1, 2, 3, 4, 5, to go from a sub 2 to a sub 7. And so, in 5 even increments from 10 to negative 20, it's negative 30. So divide that by 5, you get negative 6. Okay, there's your common difference there. Okay, or you could use a slope formula. Just do your term minus term over your number of your term minus your number of your term, and you'll get negative 6. Or you could plug both of these into the formula here and then solve this system. And we all love systems of equations, don't we? Yes, Samantha. How do I get what? Okay, so we know we have an arithmetic sequence here, right? So we've got this formula. Okay? And so what information do we need for this formula? Well, we need a first term, which we do not have. We need a common difference, which we do not have. So you have to figure out both things. Okay? So there's a couple ways to think about this. Okay, one way, like I said, like Ethan pointed out earlier, is that the arithmetic sequences are always linear. So you can think of them as lines almost, right? And you can think of this as a point, the point 2, 10, and the point 7, negative 20. And so you can use the slope formula to get the slope, which is exactly what I did right here, slope formula. Okay, that's your common difference. That's how things are changing every time, common difference. Okay, and then once you get that, it's a matter of then finding Now, in this case, you don't want to find your y-intercept. You want to find your first term. Okay, so 16. So again, you can use one of these points, plug it back in, and then solve for a sub 1, again, using the formula right there. So that's all. Yep. Jen, you got a question?
Never mind.
You're good? All right, so I got one more thing I got to show you here, and it's about series now, a series. Okay, it's very confusing. I don't like that we have two related concepts that both start with S, and they kind of sound similar too, but so it goes. So a series, okay, which you maybe have not seen yet. So this is new, I think. A series is the sum of a list of numbers. Okay? Series is the sum of a list of numbers, or you can think of it as the sum of a sequence. Okay? Now, for any one of these arithmetic sequences, if we were to take all of the terms of these arithmetic sequences, if we were to take the sums of all the terms of any one of these arithmetic sequences, what would we end up with? If we were to take a sum of any arithmetic sequence or any arithmetic sequence, if we added up all the terms, every single one of them, the entire, all of them of the sequence, what would we add up to? Infinity or negative infinity, right? Positive or negative infinity, depending on whether the numbers are positive or negative. Okay? And so when it comes to arithmetic sequences, we're only going to add up a finite number of them, okay? Because adding up an infinite number of those numbers, of course, will go to positive infinity or negative infinity, right? And so we're only going to do a finite series, okay? So again, just to sequence looks like this, right? A sub 1, A sub 2, A sub n plus 1, okay? A series looks like this. A sub 1 plus A sub 2 plus ... plus A sub n plus A sub n plus 1 plus ... And you're going to keep adding here, potentially. Okay? Now, this is a lot to write out, right? Because how do you write out, like, a long list? It's a lot to write out. Always having to write all these pluses and stuff like that. So mathematicians came up with a shorthand way of writing this, okay? And it is a way that you will need to be familiar with, okay? Because there are going to be questions on the homework and stuff like that that will be denoted in this way. All right, so the Greek letter sigma, capital sigma, which looks like an M kind of rotated 90 degrees, okay? Sigma is used to represent the sum of, okay? Sigma, sum kind of thing. Both start with an S, or the S sound. Okay, and the way we use this is we're going to add up a sub I, as we're using another variable there, okay? And sigma has a starting point. Like the sigma tells us what term we're going to start with. So in this case, we'll start with 1, because that's where my series started here. And we'll say then I equals 1 to show where we start. So we start from the bottom, and then on top, it tells us what to count up to. Okay?
Wait, so sigma is the whole thing?
It's, yes, sigma, and then you have your sequence, or your sequence right here next to it.
Oh, okay. So
A sub I, yeah, is like again, it's the same idea as our sequence here. It's just we're using an I because it's I is like our variable that is counting from 1, then to 2, then to 3, then to 4, all the way up to, and we'll say it counts up to n in this case. Okay, yes, I know we go to n. I know we go to n plus 1. Maybe I should do that. Bless you. Yeah, I mean, I can still be represented by n as well, so I don't need to be confusing. But this top number tells us where to stop, okay? So just as a real quick example here of like what I mean by that. So let's say, for example, that, okay, let me just show you a brief example of what I mean by this. Okay, so this one should be very familiar to us. all right, it's going to be, well, so let's just write it out, okay? So if you'll look here, so we're going to do a sum, right? Sigma stands for the sum there. Our I starts at a value of 1. So our very first term is going to be what value? We're adding up just i's. So what's our first I value? 1. Okay, for the first term, it's just 1. Okay, but then we're going to add to it the next term. After 1 comes 2, right? And again, why is it 2? Because the sigma here, we're just going to count. I starts counting at 1, and it counts up to 100. Okay, and so then the next I after 1, the next value will be 2. We just put 2 in here for the I. There's nothing we do to that 2. It's just the number itself, so we'll put a 2 there. Okay, and that's a sub 2. And then, of course, the next one you can guess is going to be 3, and then so on and so forth, all the way up. And then where do we end? At what number? Okay, not any number. Look at where the top number here, it tells us to stop it at 100. So we're going to go all the way up to 100, and there'll be no more terms. So this is not an infinite series. It does not go on forever. Okay, it stopped at 100, so it's finite. And so there's the 100th term. Okay. If we wanted to take one of our series or sequences from earlier, we could also sum those up. So let's see here. For example, the very first example that we did here, I could write, the sum from, I equals 1 to 4 of 4i minus 1. Okay, like that. That was our very first sequence there. Or another way you could write that is to say a sub n is equal to 4n minus 1. And so then the sum of a sub I, like that. Okay, so you could write it just like this with the sum of the 4i minus 1. Again, this was the very first sequence that we did there. Okay, or you could say a sub n is 4n minus 1. Bringing the actual sequence formula there. But then we can say, okay, if I want to add up those 4 terms, then our first 4 terms, then I'm going to use a sub I from 1 to 4. Okay, and so the I will be 1, then 2, then 3, then 4. Okie doke. So what would this look like? So again, if our sequence is 4n minus 1, but we're going to be adding up those terms, so the first term is I equals 1. Okay, so 1 would go in for the I, which is just going to go in here. Okay, 4 times 1, and I can write it out here. 4 times 1 minus 1. Okay, that's my first term. Plus my second term, now I will be 2. So it's a sub 2. 4 times 2 minus 1. Okay, and then we'll do the third term, a sub 3. 4 times 3 minus 1. And then the fourth term, last one, a sub 4 there, 4 times 4 minus 1. Okay? And so how do I know when to stop at 4? Because we go from 1 to 4. So first term, second term, third term, all the way up to the fourth term, and we stop. And I'm just using the sequence there. Okay, you'll notice if I had used this, it'd be the same thing, right? I put a 1 in for the I, so it'd be 4i minus 1, or 4 times 1 minus 1. The second term would be 4 times 2 minus 1. Next one would be 4 times 3 minus 1, and then 4 times 4 minus 1. Okay, so those are your 4, that's your expanded out sigma notation there. Okay, so questions on any of that? That's how we expand it out. Not on the quiz. It'll be on the test, though, on Thursday. Thursday's test. So, right, so we could then come up with this sum here, right? So let's go ahead and find the sum there, right? Now, we already know these terms from before. This is 3, right? And then 7, and then 11, and then 15. So we're just going to add up those 4 terms. So 10, 26, so 36 is our sum there. Okay, the first 4 terms, the sum of the first 4 terms of this sequence, okay, or in other words, the series from 1 to 4 of this sequence is 36. Okay, the sum of that is 36. Finite. Okay. What about the sum of the numbers from 1 to 100? How might we go about doing that, right? That would be a lot of work. So the brute force method, right, would be to do 1. Plus 2 is 3. Plus 3 is 6. Plus 4 is 10. Plus 5 is, and you get the idea, all the way up to plus 100. That's a lot of work. but there's a formula. And actually, there's a bit of a trick to it here, too. So I can kind of show you here what I mean by that trick. This problem, there's a legend behind this problem, actually. Okay, there's a famous mathematician named, starts with a G, and now it's blank. I'm blanking on it. No. Did I write it down here? No, of course I didn't. Anyway, no, it's like he's like Austrian or something like that. It's like Gauss. 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 Okay, so Gauss was a brilliant mathematician, even at a very young age. Okay, so the legend goes that his elementary school teacher was getting fed up with the class, and so decided to give the class some busy work so that they could get some grading done or just have some peace while they're busy doing some calculations. So the teacher was like, they only really know like addition, so I'll just have them add up like the first 100 numbers, and that'll take them a little while, and I'll have a little break or whatever kind of thing. But no sooner did the teacher give him the problem, but Gauss came up and gave the teacher the answer. Because Gauss did not do it like every other student was doing it, which was doing 1 plus 2 plus 3. Gauss instead saw, well, if we are going to add up the first 100 numbers, okay, I will do it again, but this way I will write it backwards like this. So we're going to add the list of numbers twice. But why is that beneficial? Well, what's 1 plus 100? 101. What's 2 plus 99? 101. 3 plus 98? 101. So on and so forth, on down the line, all the way to the very last term where 100 plus 1 is 101. So rather than add up all these numbers, 1 plus 2 plus 3 plus so on and so forth, all the way up to 100, he saw that, well, if I did it a second time, it would essentially be multiplication, right? There would be 100 101s. Right? And so he just did 100 times 101 and got the final answer. And that's right. Okay? That was it. So the formula, okay, the formula then, so let's see, so what do we have to do here? You take your, and I'll just write it down here. So the sum for an arithmetic series, a finite arithmetic series, okay, formula. So what did he do? He took the first term, and he added the last term. So you need to know the first and last term of the series, if you don't, or of the sequence that you're going to add up. Okay. So if you don't know the first and last term, you need to go back to the arithmetic sequence formula, find the last term, and then you can go from there. Okay. But that wasn't it, right? Because he had too many terms. So you had to take the number of terms and then divide it by 2 there. Okay. Times that. Okay. So again, what did he do? He took the number of terms, okay, times the 101, right? So there's 100 terms, and then it adds up to be 101 there. So 100 times 101, but that would give you twice as many numbers, right? Because he added 2 of them. He doubled it, kind of thing. So we had to divide by 2. So there's the formula. Okay, so n is the number of the terms. Okay, a sub 1 is the first term. And then a sub n is the nth term. Okay, whatever that happens to be. So again, if you want to find, if you want to find like the sum of the first 1,200 terms, then you need to find the first term of your sequence and the 1,200th term of your sequence using again that sequence formula that we've got from before. Did I leave it here? Okay, using the a sub. Where is it? Right here. Okay. So, all right, so let me show you one example here with that. I'm going to squeeze it in. Given the sequence, a sub n equals 2n minus 6. Okay, so that's a sequence. In other words, it's a list of numbers. Find the sum of the first 150 terms. Okay, given the sequence, that's talking back to what we talked about before. A sub n equals 2n minus 6, that's linear, right? It would come with a list of numbers, so you could plug in 1 to find the first term, 2 to find the second term, so on and so forth. But now we want to find the sum, which means we're really trying to evaluate a what? A sum of a sequence is known as a series. So we're trying to find this series here. Okay? So, n over 2 times a sub 1 plus a sub n. That's what we're trying to actually evaluate here. Do we know any of these pieces of information? What's n, for example? That's going to be 150, right? Over 2. What's a sub 1? Ooh, we don't know what our first term is, do we? But how can we figure it out? Yeah, plug 1 in here for this sequence formula. So a sub 1 equals 2 times 1 minus 6, so negative 4. Okay, so negative 4 is our first term. And in this case, our n, what is our nth term, or what's the last term we're going to add up here? 150, right? 150th term. So we're going to find the 150th term by doing 2 times 150 minus 6. So that's 300 minus 6, or 294.
Could you just go over real quick what you just did? You were moving kind of fast, so I was trying to figure out if what you were writing, because I couldn't figure it out.
Okay, well, let me finish this and I'll come back. All right, so now it's just a bunch of arithmetic. Okay, so negative 4 plus 294 is 290, and then 150 divided by 2 is 75. So it's 75 times 290, which I think I have it written here. Yes, 21,750. 21,750. Which is equal, right? That is then the sum from 1 to 150 of that sequence. Okay, 2i minus 6 right there, so I'll zoom in on that.
That was a lot.
Okay. That's just, that was a scribble. That's a scribble right there. Scribble it out. No, I can start wherever. But because we're starting with the first, because these, we tend to start with the first term, then I equals 1. But you can start adding from the second term or the third term or whatever. So we won't worry about that too much, though, for our class. Okay?
How do you find the equation of the
Equation of the sequence? Just right here? Let me see it. This one. When it is given to you, then you will have enough information to figure it out. Okay, you'll have the first term, you'll be able to find the color difference, something like that. All right, so Jenny, you had a question. You said yes.
So
Just walk back through it again.
yeah.
Okay. So let me. There we go. Unfreeze it there for myself. All right. So big picture, right? We talked about two different ways, or two different kind of like ways that patterns can be expressed, or I guess so, or kind of mathematical things with patterns. One is a sequence, where it's just like a formula that describes the list of numbers and how you find every number in that list, kind of thing. So here is that. That's what we were talking about earlier, right? Where we just like, if I want to find the fifth term, I plug in 5 for n, and that'll give me the fifth term. If I want to find the 100th term, plug in 100 for n, that'll give me the 100th term. Is that okay so far, so good? Yeah. Like that's, I could list out the numbers, a list of numbers. But then it says find the sum of this. So now we're going to take those lists and we're going to add up every single one, and we're going to add up to the 150th of the terms. Okay? So the first term, which I found right here by using a sub 1, the first term would be negative 4, and then I'll keep adding 2, and plus 2, plus 2, plus 2, plus 2, all the way up to the 150th term, which gives me 294. Following me so far?
Yes.
So I have a list of numbers that starts at negative 4, and it goes all the way out to 294.
Yeah.
Okay, I'm adding 2 every time to get between those. All right? I'm going to take those and add them up. Add up all 150 numbers. Add them all up. Okay, that's the series, the sum. Series is the sum of the sequence.
So then you go to this.
We go to this formula because it's a finite arithmetic series that we've got here. Finite because there's not an infinite number of numbers, just a finite number. And then we have the first term, which we found, negative 4. We found the nth term. In this case, our nth term is the 150th. It's where it ends. So 150th term. Okay? And the number of terms is 150. So you just plug them all in, simplify, and then that's the sum. Instead of having to do, negative 4 plus negative 2 plus 0 plus 2 plus 4 plus 6 plus blah, 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 all up to 294, the formula gives us the final sum there. Okay, and that's our answer. Yes. So not today then? Okay. The other thing here, folks, is I'll give you the homework, okay? I would strongly encourage you to work on the homework tonight, okay? Very much so.
Homework, or is it to sign in person?
Yes, sequences and series are going to be the homework for tonight. All right, page 648, 85 to 89, 103, and that's the odds. I think this is all sequence related there. And then if you want some series practice, page 657, 5 to 19, 59 to 69, and 91, and those are all odds as well. Okay? And for both of these, use your calculator. Calculator active. Okay? For both of those. Alrighty. You will also be given the arithmetic series formula as well. Okay? So you want, well, you're welcome, yeah. I mean, it's not my generosity, it's the people that decide these things. But you're welcome. I guess I could decide to make it harder, you know, kind of thing.
Oh my god, why is so cool?
You
Thanks,
put us
Jan.
both off the separate. You put us off the separate.
I didn't know what that was.
Mr. Wade, did you give me 90%?
I got you now, yes. Any other set requests? Set requests? Not today, but perhaps tomorrow. Because today we just did a bunch of like testing and stuff. So today will be like we're learning new material. Starting tomorrow, though, I might need you. So.